All right, welcome. I'm sorry if there's any background noises. I'm currently in the school library recording this, so apologies ahead of time, but we'll try to get through it. Oh, what are we talking about? Today we're going to talk about projectile motion. In particular, we're going to be dealing with two-dimensional projectile motion. So, first, what is a projectile? Projectile is defined to be an object that's in free fall. Alright, so remember, free fall is when only an object is under the influence of gravity, no other forces. So it's only accelerating because of the acceleration due to gravity. So, if that's the case, this object's in free fall, and that's a projectile. So this means technically we've already talked about projectiles, and when we talked about just objects moving one-dimensionally in free fall. But now we're going to just be looking at two dimensions. Trajectory is the path at which a projectile takes. So typically when we use the word projectile, we usually mean something moving two-dimensionally or actually three-dimensionally, which we're not going to get into. And what's really interesting, and I'll show you on the next slide, is that for an object that's in free fall, if it's moving two-dimensionally, it's going to be moving in the shape of, its trajectory will be in the shape of a parabola, or at least part of a parabola. So you can see that here. So we've got images where you have consecutive photos being taken at equal moments in time. So we have a ball that's falling, bouncing, and you can see the consecutive bounces. You can see the parabolic shape here very clearly. And similarly here for someone throwing a basketball, although there is air resistance in both of these, the air resistance is so small that it basically doesn't really have an effect on the trajectory. So we'll say both these objects are in free fall. So we have parabolas going on. Alright, so we have a video here put on by, I believe it's the MIT physics department, but it's called the shoot and drop. So what we see here is a billiard ball with a hole drilled in, and they rigged it so that when that lever is released, one just drops straight down where the other billiard ball gets hit by something and it shoots off. Sorry, I accidentally messed up the clip. So we'll take a little moment here, and he hits the lever, and we see the object dropping and the object shooting off at the same time. Let's take a little rewind here, and let's look at that motion again. So hopefully what you noticed here is that both these objects hit the ground at the same time. And actually, if you kind of track their motion, they kind of fell at the same rate. Right? If you kind of draw a horizontal line, they always meet up. Alright, so if we were to kind of, again, take consecutive pictures at equal moments in time for each of these objects, we might see something like here on the right. Right, where we have the object dropping and an object being launched horizontally. What you'll see is actually the horizontal motion of this yellow ball here has no influence over the vertical motion, and vice versa. These aspects of their motion are completely independent of each other. Right? The horizontal motion does not affect the vertical motion, and vice versa. The reason for this is because the acceleration due to gravity, so the only acceleration involved here is straight down. So that does not affect the horizontal motion at all, because the acceleration only affects the vertical motion. If the acceleration due to gravity did not point straight down, and it, let's say, pointed... If, for example, the acceleration due to gravity for some reason was horizontal instead of vertical, well then we'd have only the horizontal component be affected by acceleration and not the vertical. If acceleration due to gravity was kind of at an angle, not pointing straight down, but kind of askew, then we would have that affect both the horizontal and the vertical motion. But that's not the case. The gravitational acceleration points straight down. So that only affects the vertical motion, not the horizontal. So this is a very useful consequence, because then we can think about its motion kind of separately with the horizontal and vertical. Whoops, sorry about that. So projectile motion is made up of two independent motions. So we have uniform motion at a constant velocity in the horizontal direction and freefall motion in the vertical direction. All right, so the horizontal and vertical components of projectile motion are independent of each other. The common thing with both these, how they kind of relate to each other, are moments in time. So let's look at, sorry, I keep right-clicking. So let's look at this graph here. So this is a graph of an object's trajectory. So notice our coordinate system here is position versus position, vertical and horizontal. And we're so this is an object in free fall. So the acceleration due to gravity is straight down. And that's the case at every single point. So this is an object that is, let's say, shot from the ground. It's shot up at an angle. All right, that's what this theta naught here is describing. So it's shot off at an angle, and this is its initial velocity vector, right? So it's saying that at this moment in time, we can represent its velocity by an arrow in this direction, right? So this velocity vector is actually a vector that's drawn tangent to its trajectory at that moment in time. So we have this initial velocity vector. And as it raises up, so I'm just looking at the total velocity here. So as it moves along its trajectory, let's analyze this moment in time. All right, so our velocity has slowed down. We can see that by this arrow for velocity getting shorter. And we know that just by kind of looking at an object. It slows down as it reaches its peak. All right, and then at the top, all right, its velocity is actually going to be the smallest in magnitude. And we see that this length of this vector is the shortest compared to everywhere else. And then now our vector starts to kind of point downward because it starts to move downward. And it starts speeding up and so on and so forth. You see here we do have a symmetry, right? So our initial velocity at this point in time here is equal to the velocity when it hits the ground over here. At this height here, this velocity vector is equal in magnitude to this velocity vector. We have symmetry about the peak. Now, if we were to break up these vectors into its horizontal and vertical components, we can analyze that throughout the motion as well. So let's look at horizontal first. So horizontally, we have no change in this object's motion. So we see that here, its initial velocity, we break up its x component. This vector is the same at every moment in time in its travel. So if we were to track just the horizontal motion at every moment in time, our object's going to travel the same horizontal distance. All right. Now the vertical component of this vector changes, and that's because we have acceleration going on. So initially the vertical component of our initial velocity is a large upward vector, right? The acceleration kind of, so to speak, eats away at that over time. So as it travels, since the acceleration points downward, our upward velocity gets shorter or smaller in magnitude until a point where it reaches a value of 0 at the peak. So at the peak of an object's trajectory, its y velocity, the y component of its velocity is 0, which is actually what we saw in 1D motion. So just be careful. A lot of times you might think, oh, at the object's peak it's not moving. That's only the case if we're analyzing the vertical component of its motion. So if an object's only traveling straight up and down, yes. But since here traveling two-dimensionally, its y component is 0, but its horizontal component is not. It is still moving at the peak. It just has no vertical component of that motion, just the horizontal. Anyway, so now the velocity becomes in the downward direction, so it's speeding up and so on and so forth. All right, so we do have some nice symmetry going on, and we can use vector components to kind of analyze what's going on in the situation. So quick question for you. So let's suppose we have a ball with a mass of 100 grams and it rolls off a table and lands 2 meters from the base of the table. Now a 200-gram ball rolls off the same table with the same speed. How far will it land from the base of the table? So hopefully you said that it will land 2 meters from the base of the table. Right? This is because the gravitational acceleration, things fall at the same rate no matter what the mass is, assuming we're in free fall, which was what we're assuming here. So even though these objects have this different masses, since they're launched off the table with the same speed, everything kinematically behaves the same. So they'll land at the same spot. All right. And kind of, is this the last thing I wanted to talk about? One of the last things I want to talk about here is the range of the projectile. So we can manipulate kinematic equations to give us a formula for the range given an angle, and hopefully I'll still have a lab activity for you that involves that. It's pretty interesting to do. But range is a word that means how far an object will travel. Typically when we say an object's range, it's going to be the distance from where it started to where it lands on the ground, typically. So that's what range means. Now, just based on how the math works out, maximum range is going to be achieved at a 45-degree angle. And this graph here is hopefully going to show that. The other thing you can see from this graph is that we have a symmetry going on here. We see here that angles of theta and 90 minus theta give us the same range. So for example, a 60-degree angle here for initial condition of something being launched at a speed of 50 meters per second gives a range of 225 meters. Whereas 90 minus 60 being 30, if you look at the 30-degree range, we also get 225 meters. So it'll be interesting to see why that's the case. And again, I'm going to step you through that in a lab activity. But we're basically at the point where we should probably look at some problems and how to solve them. So some problem-solving strategies. First is to draw a diagram. You want to label the beginning and ending points of a motion. So whether that literally be the start and end of the motion, or kind of subdividing the problem into different points in the object's motion that are important, right? So sometimes that might be its starting, its peak, and its ending. You want to set up a coordinate system. So this time, since we're dealing with 2 dimensions, you want to label an x and a y direction as being positive. And then you start defining your knowns and unknowns, right? So we are going to have 2 lists now, one for the horizontal components and the vertical components, right? So I kind of like to list that as horizontal stuff and vertical stuff. So we're dealing with basically kinematics, but rather than just 1 dimension, 2. So it's not anything more kind of difficult than what we've done. It's just another step. Now, kind of the key in problem solving is relating what's going on horizontally to what's going on vertically. And the key in doing that is going to be realizing that when we're looking at the time doesn't have components, so the time is what's going to relate the 2 things. All right, so we'll move on here to look at a couple of problems and break those down, and hopefully things will come together a bit more. Thank you.